Stage is yours. Thanks for being here.
Can everybody hear me? Great. Firstly, thank you to the organizers for having me. It's really lovely to be here and get to meet everybody. Thank you to Philip for giving me some of his time so that I can have a longer talk. He didn't know that, but he does now. But yeah, it's a pleasure to be here. I'm looking forward to chatting with folks over the rest of the week. So what I'm going to tell you about today is ongoing work in my group and in a close collaboration with Dave Schuster in his group in cavity QED for everything. Fundamentally, what I would say is that if there's something that I like about quantum science, it's that it's an excuse to make cavities and couple them to things. And so, my group has focused both on using cavities, arrays of cavities, multimode cavities as a way to study condensed matter physics, both in the optical domain and in the microwave domain, and for quantum information type applications like quantum transduction. Our main focus for today is going to be making quantum matter out of microwave photons. This is again a close collaboration with Dave Schuster's group, and at the end I'll have a quick one-slide shout-out for our recent result on atom-mediated quantum transduction. Okay, so I like to always start, before I start telling you about the quantum materials that we made, with a couple of slides just briefly setting the stage in terms of when I say we're going to make a material out of light, what do I even mean by a material? My mom likes to ask when I'm going to make her a sweater out of photons. We're not looking for that scale. But the basic point here is that when I say a material, I just mean some collection of particles that can interact with each other and thereby sort of organize or order. And so the picture you should have in mind, each of these little dots is a particle with some mass, okay? And it is attracted to each of the other particles when it's far away from that particle, and it's repelled when they're close together, and there's a tiny little bit of friction in this model. So if you let this evolve, that's all you need to get a crystal. You can see phonons in this crystal, you can see the crystalline structure, and so forth. Okay? And again, the ingredients that we needed was a collection of particles, and by particles I mean objects that respond to forces in some sensible way. We need some interaction potential between those particles, okay? And then finally we need some way to suck entropy out of the system, in our case here it was friction, to build some interesting manybody state. So if you're going to try to make matter out of light, you run into a couple of generic problems. The first is that if I have an electron or a baseball and it's moving to the right and I apply a force to the left, it slows down and then turns around and goes back to the left. Okay? By contrast, if I have a photon moving to the right and I apply a force to the left, well, it turns out it just changes color, okay? Which is not actually what particles in a material do. And so we need to fix that, and there's a sort of simple way to understand this, and this is that the energy-momentum relationship of a photon is linear. Okay, and this is problematic because when I apply a force, all I do is change the momentum of the photon, and if this slope is the same at all momenta, that means that the velocity doesn't get changed by the force. Now you can say, like, John, that was obvious. We already knew that. Photons always move at the speed of light. But of course, this tells us that if we trap the photons in some sort of a metamaterial, we can change the dispersion of the light and make the photons act as though they have a mass and can respond to forces and so forth. Okay. The second challenge is that if I have two electrons, when they move towards each other, they can collide and fly apart. If I have photons, that's not quite the story. You know, Maxwell's equations are linear, so if I have a photon moving to the right and a photon moving to the left, then when I have both of them, the sum of those two solutions, they just go through each other. Okay, so this is a problem. We need a way to add interactions between these photons. Of course, we can now go back and say, well, how do electrons really collide? Well, quantum electrodynamics says they collide by exchanging virtual photons. So you might say, can I make my photons collide by exchanging virtual electrons? This Feynman diagram is disallowed by all of the conservation laws, but you can draw some kind of a higher order Feynman diagram which is allowed. This one is quite small, but the idea is correct, okay? The basic idea here is to use matter to mediate interactions between photons, much as the natural world uses photons to mediate interactions between atoms. Okay, so this brings us to the main topic of the day, which is how do we make materials out of microwave photons, and what sort of interesting science can we get from that? Okay, so if you get nothing else from this, I think a really nice set of takeaways is trying to make sense of these basic questions. How are we making photons act like they live in a lattice? How are we making them interact with one another? How are we managing entropy and cooling the system towards some interesting manybody state? And again, this experiment is a close collaboration with Dave Schuster's group. So we want to make a lattice site for photons, much as an ion is a lattice site for electrons. So what is an object that holds photons very nicely? It's an LC circuit or a microwave cavity, whatever you prefer. Now, if we quantize that circuit, and imagine I choose 1 over root LC to be 4.5 gigahertz, now I have a situation where the eigenstates of this circuit are 0 photons and 1 photon and 2 photons and so forth, and they're all separated by that 4.5 gigahertz energy. Okay? So in some sense, we're in good shape. The downside here is if you think about an electron trapped on an ion, right, the spectrum is quite anharmonic. The energy required to put one electron onto that ion is quite different than the energy required to put another electron onto that ion due to Coulomb repulsion between the electrons. So we need to make some kind of a circuit element here where this spectrum is anharmonic, because that's, in this lattice model, what collisions look like between the photons. So the question is kind of, how do we do that? Now, for those of you who have ever built an LC circuit, how many theorists do we have in here? And how many of you have ever built an LC oscillator? None of you ever? You didn't have to take undergraduate labs? Okay, a couple of you. The rest of you make me sick. You're not recording that, right? He is recording. That's too bad. Oh, hi. Okay, so if you've ever made an LC circuit and measured its spectrum, what you find is that if you drive it hard enough, right before it gives up the magic smoke, the frequency of that resonance starts to shift. Now, why does that resonant frequency shift? Probably because the inductor is heating up and deforming, and that deformation leads to a change in the inductance, which shifts the frequency. Okay? And so this is great. That gives us the frequency shift that we want. The problem is there we needed 10 to the 15 photons or something. And of course, if you're trying to build up entanglement, as soon as you lose one of those 10 to the 15 photons, you're entangled with your environment, and the quantum coherence of the system is effectively lost. So we would really like to be able to see that kind of physics with many, many fewer particles, in this case photons. So the natural thing to say is we should make this inductor smaller so that it requires less heating. Okay? Now, heat in general is a bad thing, but this is kind of the right idea. The ultimate limit of that is to replace the inductor with a Josephson junction. Okay? And the way you should think of this Josephson junction, if you're like me, mostly a cold atom person, is that the Josephson junction is an inductor whose inductance depends very, very strongly on how much current is flowing through it. Okay? And as we learned earlier today, this Josephson junction is basically 2 aluminum wires that cross with an aluminum oxide tunnel barrier between them. Okay? And then some superconductivity happens and that pops out. So what's the... for more details, see Dave Schuster's thesis. There really is a very nice explanation there. But the upshot that I want you to take away here is this object, this nonlinear LC oscillator, this Josephson junction capacitor oscillator, can have a 0 to 1 photon transition at 4.5 gigahertz and a 1 to 2 photon transition at 4.2 gigahertz. So this says we have like 300 megahertz of attraction between the photons in our system. Interestingly, this object is also called a transmon qubit. Okay, and the reason you say, but it has 3 levels, John, in what sense is it a qubit? The basic point is that I can drive Rabi oscillations on this transition without exciting myself up to this doubly excited state due to this anharmonicity of the system, so it makes a very good qubit in the same way that an atom makes a very good qubit. I think I need to stand more this way so that I don't get roasted by that light. Or I need a towel or something. Okay. So we know how to make our lattice site here. Suppose we want to have tunneling between lattice sites, because again, if you're going to try to make a material, you do need to have tunneling between the ions or the ion analogs in the material. I swear I'm not checking my email. I'm just trying to stay on top of the timing. Great, there we go. No exciting emails. Okay. The way we achieve that is just by lithographically patterning a capacitance between the adjacent lattice sites, okay? And so this allows the photons to hop from one site to another. For the story I'm going to tell you today, we pattern about a 10 megahertz tunneling rate for photons between the sites. And now we're in a situation where we can have a bunch of these sites in a row, and this gives us like a 1D Bose-Hubbard model because the photons are bosons. So the natural question that you ought to then ask is how long do the photons live in this system? And for us, they live about 40 microseconds, which gives us time for about 12,000 collisions or 400 lattice sites of tunneling, which incidentally is sort of comparable to what can be achieved in cold atom systems in terms of these unitless quantities. An interesting thing, long-term, what we would really love to do is take advantage of these advances in transmon coherence that you heard about earlier in the day, and get this number up to 400 or 500 microseconds or a millisecond, and then you can study even larger systems before you're dominated by decoherence or loss. Okay. So this is what the object actually looks like with a little bit of extra color here. Each of these objects is one of the lattice sites, one of these transmon qubits. They're coupled to one another capacitively here, just by the gap between them. And then we can measure the occupancy of each lattice site using cavity QED techniques. This meandering coplanar waveguide acts as a cavity that's capacitively coupled to the transmon qubits. So for the cavity QED people in the audience, the cooperativities that you can get in circuit QED, at the low end is like 1 million, at the high end is like 100 billion, right? So what it means is that you can just use the cavity QED kind of techniques as tools for readout rather than as the science itself in this platform. Okay. So we've got, here I've shown 4 lattice sites. We've got tunneling between these sites. We've got some on-site Hubbard U. We put this thing in the dilution refrigerator to cool it down. I told you that the interaction energy on the site is much larger than the tunneling rate, so we should get a mod insulator here, right? Well, the ground state's actually no photons in the system, right? So if you just do that, you get nothing. That's like saying if I shine 2 laser beams, or 6 laser beams into my vacuum chamber, I should get a mod insulator of rubidium atoms. Well, you have to also add the rubidium atoms to get that to happen. Unfortunate. Little known fact, the first experiments, actually they forgot to add the atoms. I made that up, that was not true. Okay, so instead of trying to sort of mimic the adiabatic preparation approaches for mod insulators that the cold atom people have tended to take, I'd like to tell you about a different approach. Suppose, exactly, that's actually flow K modulation. Did you see that? You're getting some Bessel renormalization of the tunneling. Okay, we need a magical object here that sort of autonomously refills itself to always have 1 photon. And what I'd like to argue is if we have that object and we couple that to our system, we'll prepare a mod insulator over here. So how does this work in practice? The idea is that this photon will hop into the system, this object will refill itself, and now the next photon can't hop into the system due to the interaction between the photons, till this first photon hops over, and then another one can hop in, and this thing refills itself, and so on and so forth. So in some sense, what I would call this is like a chemical potential for light. It provides photons at this particular energy irreversibly to the system. But the question is, how do we make that object? Okay? And this is a sort of reservoir engineering. We need some kind of an object that, whenever it has 0 photons, refills itself to having 1. It's just like an inversion in a laser. So what we need to do is have, you might say, well, John, why don't we just drive it with a laser from 0 to 1, right? Microwave drive, that should be great. Well, the problem is, once it's in 1, that same drive will bring it back down to 0, right? So we need some irreversibility in the system, right? We need to do some kind of optical pumping. So what we'll do is drive from 0 to 2, and then we need this 2 state to decay really fast. This is how we make an inversion in a laser. But the problem is, the 2 state in the transmon decays twice as fast as the 1 state, but that's it. That's not enough. We need a bigger decay rate here. And so what we need to do is couple this object, which so far is just one of these transmons, to an RLC circuit that's resonant with this transition, but not with that transition, right? And the cool thing is, we can lithographically pattern this object, right? And then couple it with capacitors and realize this kind of a non-Markovian damping, non-Markovian meaning frequency dependent or damping with memory to our transmon, and then just have that drive. So what does this look like in practice? Basically, what I'm going to show you is the occupation of each of the sites in a 7-site system when the chemical potential is at the right end versus time. So we start empty, the system then fills up to 1 photon per site in a few microseconds. So this works very nicely. And just to get a little bit more flavor of what's going on here, you might say, what happens if I remove a particle from the system? Well, if I don't have this refilling site, then this hole just randomly walks back and forth across the system. This is sort of the complement of this transfer data that we saw earlier today. But if this refilling drive, this chemical potential is on, then the hole can only walk until it gets to the refill site, and then it gets eaten, and basically you go back to 1 particle per site. So this is sort of a different regime than we typically think about operating in as cold atom people, because this state will persist indefinitely. Okay, so the next question that I want to ask is, can we make fluids in this system? Well, the problem is that chemical potential object that I described to you will put photons in until the system kind of fills up to some compressibility gap where the energy required to put a photon in changes substantially. And then it will stop putting particles in. And these fluids, where there's less than 1 photon on average per site, tend to be compressible. Okay? So as a consequence, those techniques are not going to work, and I'd like to show you a sort of different kind of an adiabatic technique that does work and leads us into, I think, some pretty interesting ways of making macroscopic superposition states, and that's kind of what we'll finish with. So imagine that I want to generate the lowest energy state of the system without disorder, some delocalized particle in a box state with 1 particle. Okay? One way to do that is to start by putting disorder into the system, such that each lattice site is at a different energy from all of the other sites. And then, if I want to put a particle into the highest energy site here, I can just have a microwave drive on that site, and that'll put a particle in. And that actually is the highest energy eigenstate of the system, right? Because we have this disorder, the eigenstates are all localized. So the thing that's now quite interesting is that if I adiabatically remove this disorder, I go from the highest energy state with the disorder into the highest energy state without the disorder, which is a photon delocalized over the whole system. Now, to be clear, you might say, John, why are we talking about highest energy states, not lowest energy states? Well, remember I told you initially that our interactions are attractive, rather than repulsive. Well, our tunneling is also negative, and so everything's kind of flipped. But basically, it doesn't affect the story. So we can play the same game. We can put a photon into the second highest energy lattice site, adiabatically remove the disorder, and go into the second highest energy eigenstate. In practice in the lab, when we do this, if we pi pulse a photon in here and look at the distribution of the photon over the system that we get versus disorder, the photon delocalizes, and we end up with, this is actual data, this single particle in a box state. Works very nicely. Similarly, if we put the photon into the second highest energy site, we get the second particle in a box state. So this all works very, very nicely. I think for the sake of time, I'll skip this piece. And indeed, we can play this same game, and this is very fun, with multiple photons in the system, right? If I put particles into these two sites, that is the highest energy state of two particles, right? And then I can remove the disorder and go into the highest energy state with two particles where the particles are now delocalized, they're entangled, they're avoiding each other, so forth. So these are Tonks gases. We can do this with 2 particles or 3 particles or 4 particles and so forth. And indeed, if you look at the correlation between the particles, this G2 kind of says if I detect one of the particles at a particular site, what's the likelihood of detecting the other particle some distance away? And what you see is that basically you get a universal behavior that you expect for a continuum Tonks gas where the separation is sort of set by 1 over the average density. Okay. The fun piece here, I think, is to try to make superpositions of few body states in this system. So how does that look? Well, what we already did was pi pulse particles in one by one, and if we just pi pulse the particle in and measure, we get a localized particle. If we remove the disorder, it delocalizes. We can repeat that for a second particle and for a third. But what if instead I pi pulse the first 2 particles in, and I drive a pi over 2 pulse for the third particle, and then I remove the disorder? Well, you can see without removing the disorder, I get kind of the average of the 2 possible outcomes. Half the time I have a particle here. And if I do remove the disorder, I get kind of the average of the 2 density distributions. But the question is there any coherence between these 2 states? And so to figure out how to measure that coherence, let me just describe an experiment for you. What we've been doing is pi over 2 pulsing this last particle in, and then adiabatically removing the disorder, preparing this superposition of 2 many-body states, and then measuring. What if instead we pi over 2 pulse the last particle in, adiabatically remove the disorder, prepare these 2 many-body states, wait some amount of time to accrue a phase between them set by the energy difference between the 2 many-body states, adiabatically reintroduce the disorder, and that leaves us in a state where the single qubit that we pi over 2 pulsed now has that many-body phase just written onto it. And now we can drive another pi over 2 pulse on that qubit, right, to perform kind of a many-body Ramsey experiment, but where all of the information is read out via a single qubit. Okay, so this is sort of qualitatively what this experiment looks like. We put the particles in. I don't know what that is. We pi over 2 pulse the last one. We melt, we hold, we freeze. We finish the Ramsey sequence and we measure. Okay, if we do this for a superposition of 0 and 1 particles, if we make the ramp nice and slow such that we're adiabatic, we get this Ramsey fringe versus the hold time. And it has a single frequency component telling us about the energy difference between that 0 particle state and the 1 particle state. Okay? If we're non-adiabatic, if we make the ramp really fast, then we prepare many different single particle eigenstates. And so this Ramsey fringe has many different frequency components in it that we can all resolve. Okay? We can do this for a superposition of 0 and 1 particles, 1 and 2, and 2 and 3. Here what I'm doing is on the y-axis, I'm plotting the Fourier transform, and on the x-axis, I'm plotting how slowly I do this adiabatic ramp. So if I'm very non-adiabatic, you can see a bunch of frequency components. If I'm very adiabatic, I just have this one frequency component corresponding to that one pair of states that I wanted to make. So we can apply these ideas to making measurements of synthetic matter. Again, the thing I just showed you is really measuring the chemical potential of the system. It's measuring the energy required to add one more particle into my many-body state. Okay? And so we can do this varying the number of lattice sites and varying the number of particles. And indeed, what we can do is actually extract this chemical potential from that frequency as a function of the particle number, or particle density. And what you see is the fluid has some added energy required per particle due to the interactions between the particles and the fact that they're trying to avoid each other. But as soon as you hit a density of 1, you hit this compressibility gap corresponding to a mod insulator. So this works very nicely. The last piece that I want to share here is that you can also use this to make and probe noon states, these states that are really useful for metrology. So the idea here is to put 2 particles onto the left side of the system and then have this middle site detuned by the interaction energy U, such that if there is a particle there, when I adiabatically move those sites down, these 2 particles can tunnel across on top of that one. But if I don't have a particle here, it costs too much energy to hop into that site, and so they just don't do it. Okay? And so what this means is, after this process, I end up either with 3 particles on this side if I did put a photon in there, or just 2 on that side if I didn't. So you should imagine this whole experiment as being, I have this pi/2 pulse, I adiabatically now, so this is the 2 possible realizations, move the lattice sites down, I wait some amount of time and acquire some phase, I adiabatically move the sites back up, and end up with this superposition state, which tells me about the energy difference between 2 particles on the left and 2 particles on the right. Okay, and we get these nice fringes. This is for this 5-site system. And indeed, what you can see is that as I vary the amount of energy difference between the left side and the right side, I can use this as a direct way to get some entanglement enhanced sensitivity. This fringe has a slope of 3, indicating that it's the fringe gives me like 3 times the sensitivity, some kind of Heisenberg limited sensitivity to fields that detune the sites. Now, we tried to do this with 7 sites. It didn't work, limited by the transmon T2. But the T2 is only 4 microseconds, the T1 is 20 or 30. So I think I won't go into this super carefully, but I will say what we've now added is a many-body spin echo to this. So instead of just having this state prep, a forward evolution, a hold time, a backward evolution, and another pi/2 pulse, we now have this, most of the time is spent on these, and that gives us a lot of dephasing. If we have a forward, a backward, and then a pi pulse on the ancilla, and then a forward, and then the hold time, and then the backward, basically what you do here is you've echoed out all of the dephasing during these pulses. You haven't echoed out the dephasing in the middle there, and this actually works beautifully. With 5 sites, it takes us from a signal that looks like this to one that looks like that. With 7 sites, we now have a signal. So just broadly, what I would say is this sort of suggests a pretty exciting future using quantum computers to probe quantum materials, even in this NISQ era. The last thing to say is we have an experiment we've been working on for the better part of a decade to use cold atoms as quantum transducers. And we've now succeeded with a conversion efficiency nearing 60%, bandwidth of 300 kilohertz in less than 1 photon of added noise. And this is the most important slide. These are the folks who really did all of the work. So thank you for your attention.
Okay, thank you, John, for that very interesting talk. I'm sure there are questions.
Thanks. Why not increase the tunneling rate so you can do everything faster?
Yeah, it's a good question. Things like readout are much easier when you have low tunneling, because to read out, we have to tune the sites away from each other, right? And so we have ideas for getting around that by adding tunable couplers between the sites, but that sort of doubles the complexity of your system, and our idea has been to avoid that. We think 20 megahertz is probably still okay.
Okay, more questions?
You mentioned with your protocol you can sense now with the Newton states and get some Heisenberg limited sensitivity of some distortions on the, basically bringing down the energy of the potential, which is kind of a flux line driver. Is there some practical application for this?
No, it's not practical. No, absolutely not practical.
You can be more better in sensing, I don't know, noise on some real lines feeding into the system?
I mean, I guess I would say I'm viewing this more as a demonstration of an idea of a way to build these states, rather than, like you work very hard to avoid having anything, you know this, go in there. So if you're sensing something, probably you should add another shield. I think you say, are we measuring flux on the lines? I think most of the flux noise is like local stuff. It's not stuff on the lines. So it's contrived a little bit, I agree.
Okay, I don't see any more urgent questions. Let's thank the speaker again. Okay, our next